Okay, now, so let us consider the concept of isospin. So there are two parts, iso and then there is spin. So why do we need an isospin? Is there any particular reason for introducing yet another spin? You see, inside the nucleus we already have protons and neutrons, right? Protons and neutrons. Now, in a way, you can consider both of them as two different aspects of a single particle, the nucleon. Different aspects of nucleon. Why? What is the difference between them? You see, what about the mass? The mass difference between the both of them is approximately 0.1% or 1.3 MeV mass difference. Proton have more mass compared to neutron by 1.3 MeV. And another difference is the electromagnetic nature. Okay, so the basically main distinction between these two particles is in their electromagnetic property. And what electromagnetic property? Don't just always say that only their charge is different. Not only charge, even their magnetic dipole moment is also different. So overall there are how many differences then between proton and neutron? Overall there are mass different, charge different and magnetic dipole moment different. Three differences. Now you see, if we are dealing with only strong interaction, only nuclear, strong nuclear force, then such differences do not appear. What do you mean? What I mean to say is that in the absence of electromagnetic interaction, a proton cannot be distinguished from a neutron. Why? Because this mass difference is very small. So the main difference is due to the electromagnetic origin in nature. Now this situation, what situation? That in absence of electromagnetic force, P can't be distinguished from neutron. Now this entire scenario is quite similar. Where? Is very much similar to the case of particles with different value of spins. Particles with different spins. MS, right? Say plus minus half. And also, so MS equal to plus minus half. They are also degenerate in energy and as a result are indistinguishable from each other. However, if we put a finite magnetic field, then what will happen? Then this degeneracy, this energy degeneracy will be removed and the particles are observed to have different energies depending on whether their intrinsic spin S is aligned parallel or anti-parallel to the magnetic field. So you see the difference between, these two cases are very much similar. Yeah, this case and this case. This is a nuclear physics case and this is a quantum physics, atomic physics case. They are very much similar. Okay. So the difference between a proton and neutron is quite analogous to the difference between particles with MS equal to plus minus half. If we substitute the Coulomb field with a magnetic field. So here we have got the Coulomb field as the culprit and here we have got the magnetic field as the culprit. So this is basic idea. Now, okay. Now, if the protons and neutrons are considered as identical particles, then we need a new level to distinguish between them. Okay, so need new level to distinguish proton and neutron if they are identical, right? And for this purpose, this isospin concept was introduced. So we introduced isospin concept. Now, since there are only two possible states of nucleon, so nucleon has two possible states, and so what we will do is that we will assign isospin T equal to half to a nucleon. Okay, using the spin half analogy system. Since they can also have two different substates. Okay. So the two nucleons are distinguished by, now if T equal to half, then what is that Z component or TZ? This is equal to only plus minus half, right, for this operator T. Now normally we choose, let me use a different color. Yes, so normally we choose T equal to half and T0 equal to plus half. T0 is basically the TZ. This we use for proton. Remember, plus half for proton and minus half for neutron. This is the usual convention. Okay, and this we write like this. So this is equal to basically the proton and this is equal to basically the neutron, where this P and N, these two, where is it? Yes, this P and this N represent the wave functions of proton and neutron. Okay, now let us consider a nucleus, many body quantum system. So what will have the total isospin of a nucleus? What will happen? Total isospin of a nucleus, capital T. So this is equal to summation I equal to 1 to A, sum over A nucleons inside the nucleus, individual isospin sums. Now you see, this is quite identical to the rule for the addition of angular momentum.